Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to the online lecture on control systems. Today we are going to discuss steady state error with respect to system type. So we have already started this discussion and I'm just going to continue this discussion beyond the point that we did last time. So steady state error for systems of different types. So first of all, I want to remind you what is a type of a system. So type of closed loop system is equal to number of poles at the origin in open loop gain. So if you have a system of let's say this configuration C of S, G of S, and here you have negative feedback and Y desired, let me use the capital Y desired of S and Y of S. This is all frequency domain. So here the difference between Y and Y desire is E of S. E of S is the error that is the difference between Y desired and Y. For this type of system, the closed loop transfer function is C into G over 1 plus C into G. This is the transfer function between Y desired and Y. So this transfer function has a type. So type of this transfer function is determined by number of poles at the origin of this thing, C into G. So if C into G has one pole at the origin, then this system will have type 1. If C into G has two poles at the origin, this system will have type 2. If C into G has 0 pole at the origin, this system will have type 0. So we have already discussed this. I have already provided you examples. I'm not going to do that again. I just wanted to remind you, and now we just get straight to the business and see what steady state error is for different type systems. So first of all, and I also want to remind you what steady state is. So the concept of steady state is time domain. So in time domain, if you have this x-axis time and y-axis y of t, and let us suppose you want y of t to achieve some value y desire, and you apply the control and the system does something like this. So here beyond this point the system has achieved a steady state. So what we are interested in is that what is the difference between y and y desire in the steady state. So this will be given by limit t approaches infinity E of t. E of t is y desired minus y. So we discussed last time that if you use final value theorem, which tells you that final value of a signal in time domain can be determined using the initial value of the Laplace transform of the same signal. So if the system is asymptotically stable, if the closed loop system is asymptotically stable, then this limit t approaches infinity, e of t will be equal to limit s approaches 0 s times e of s. And for the system of this configuration, this type of a system where this is e of s, this is c of s, this is g of s, then you have this is y of s, and this is y desired of s. So in this case, e of s is equal to 1 over 1 plus c of s, g of s times y desired of s. So the value of the steady state value will depend upon what kind of desired output you have for your system. For example, you can have a step desired value as a step, unit step, like here the constant desired value, or you can have a ramp desired value, or you can have a parabola desired value. So in each case the steady state error will be different. So if you use this transfer function of e of s, then you can calculate steady state error for the system of different types for different types of y desire. So first of all, let me show you what happens to e of s when the system has different types. So for example, if the type of the system is 0, so type 0 system, c into g will have like c of s into g of s. If you apply s equal to 0 to this transfer function, nothing will happen. So c of s into g of s, it will be in general some transfer function which we cannot do anything about. So similarly, e of s will remain equal to 1 over 1 plus c of s, g of s. But for, let's say, type 1, for type 1 system, c of s into g of s, since by definition type 1 means there is one pole at the origin, so this can be written as 1 over s into c bar of s times g bar of s. So what I've done is, like, I have taken 1 over s common from this product, because I know it is type 1, so there must be 1 over s in it, otherwise it will not be type 1. So whatever remains after taking 1 over s common, I denote it by c bar and g bar. So in this case, error will be 1 over 1 plus 1 over s c bar g bar, which will be equal to this s will become LCM, and this will become s over s plus c bar g bar. So you take s LCM, so it will go up in the numerator, and this term will become s, and this term will remain as it is, c bar g bar. So this will become, so in this case error will become so in general error will be s to the power k, where k is the type of the system. Okay, type of the system, and this will also be s to the power k. So k is the type of the system. So the expression for the error for type 2 system will be s square over s square plus c bar g bar. The expression for the error of type 3 system will be s cube over s cube plus c bar g bar. So this is important, because once we know this, then we can calculate the error, steady state error for systems of different types regarding different inputs. Now assume that for step input, So if your input is step, that means y desired of s is in general some alpha, constant alpha over s. So this is your step input. If you apply a step input, then steady state error for type 1, let's say type 0 system. So for type 0 system, steady state error limit t goes to infinity e of t will be equal to limit s approaches 0 s times e of s, which will be limit s approaches 0 1 over 1 plus c s g s times alpha over s. Alpha over s is, so there is also s in the numerator, so we'll just put it here. This s is basically this one, so this is this one. So this, you can see that this s will cancel out with this s, and this will give us limit t approaches infinity e of t will be equal to alpha over 1 plus c of 0 and g of 0. So c of 0 and g of 0 will in general be a finite value. So the steady state error with respect to step for type 0 system will be finite. So this is some finite value, finite non-zero value. Okay, so what does this tell us? That if you apply a step input to a type 0 system, in general the steady state error will be some non-zero finite value. So same if you apply to a type 1 system. For type 1 system, limit t approaches infinity e of t, this will be like same thing, but for type 1 system e of s will be limit s approaches 0, this is s, so e of s will be s over s plus c bar g bar, and if you multiply it by alpha over s, this else will cancel out, this will be an extra s due to the type of the system, due to the type of the system. So this s, if you apply the limit, then the error will be 0. Similarly, if type is higher than 1, like type 2, type 3, type 4, for type k there will be s to the power k here and s to the power k here, and then for all the types greater than or equal to 1, steady state error with respect to step will be 0. So let me summarize this. So if I summarize this, you can say that steady state error with respect to step input, this is limit t approaches infinity e of t, this is equal to alpha over 1 plus c0 g0 for type 0 and 0 for type greater than equal to 1. So this is the summary of steady state error with respect to step. And sometimes we also define something called the error coefficient. Error coefficient, this quantity is useful in some cases. Error coefficient, so this is you can denote, so each input has its own, so error coefficient for step input, is, let's say, kp, and kp is equal to limit s approaches 0 cs into gs. So this is limit s approaches. So this is basically this thing here, this is kp, this is error coefficient. So steady state error is alpha over 1 plus error coefficient. So larger the error coefficient, smaller will be the steady state error with respect to step. So this is the definition of error coefficient regardless of the type of the system. So error coefficient is not dependent upon the type of the system. Error coefficient is some quantity which is defined like this. So but steady state error is like different for type 0 and another values for type 1 and higher values. So this was steady state error with respect to step of different systems, and now we find the steady state error with respect to ramp input. So ramp input is something like this. This is time and this is y of t, and you want y of t to like follow a slanted line. So this is a straight line, this is straight slanted line. So this is basically y desired of t. So you want somehow you want that your system should follow this slanted line, and after this value in time steady state is achieved. So we are interested in what happens in the steady state. So if we do the calculations as we did for the step input, the only difference is this time y desired of s will be alpha over s square, not just alpha over s, it will be alpha over s square. So in this case your steady state error, if you calculate it, it will be E steady state, which is limit t approaches infinity e of t. I am just denoting it as E steady state. So this will become infinite for type 0, and this will become you can say this will become alpha times c of 0 g of 0. Let me just calculate it rather than writing it like this. So this will be finite for type 1 and 0 for type greater than or equal to 2. So I just want to so since the type 1 will have c bar of 0 and c g bar of 0, because we take 1 over s common, and what remains is c bar and g bar. Actually it will be inverse of that, so it will be 1 over alpha divided by c bar of 0 g bar of 0. So this is complicated enough for me to actually show you how it is derived. So for type 1 e of s is limit s approaches 0. So here also limit s approaches 0 s into e of s, s into e of s. So remember this is type 1. So for type 1 there will be s over s plus c bar g bar, and here input is ramp, so alpha over s square. So this s, these two s cancel with this s square, and this will be alpha over, so this s will go to 0 because this limit will apply. So this will be alpha over c bar g bar. This is what I have written here. So c bar of 0 and g bar of 0, because we have applied the limit s approaches 0. So I hope this is now clear. And also for the ramp input, this is basically c bar 0 g bar 0. This is error coefficient. So if you denote this if you call this error coefficient for the steady state error with respect to ramp, denoted by, let's say, k nu. So k nu is c bar 0 g bar 0, and error is alpha over k nu. So larger the error coefficient, smaller will be the error. So finally I'll do just one more input, and you can imagine what happens for the other types of inputs. So imagine we want to calculate the steady state error with respect to, let me see. Alright, so we want to calculate steady state error with respect to parabolic input. So parabolic input is y desired of s equal alpha over s cube. So for this type of input, then you have steady state error will be equal to, if you do the same steps that we did for the for the steady state error with respect to step, we do the same things, and we find that steady state error is infinite for systems of type 0, infinite for systems of type 1, and it will be something like alpha over c bar of 0 g bar of 0 for the systems of type 2, and it will be 0 for all the systems of type greater than equal to 3. So you can see a pattern already. I hope so. I hope you see the pattern already. So this here is the error coefficient, you can call it Ka. This is error coefficient for parabolic input. So parabolic input is something like this. If you draw it in the time domain, you want your system to follow this parabolic curve. So system will do something like this. It will try to follow, or maybe it will fall apart depending upon its type. So once the system settles down, whether the steady state error is infinite, finite, or 0, all depends upon the type of the system. So now I'm just going to summarize all of what we have discussed so far. So what is the summary? Okay, so summary of steady state. Acha ji. So for the system of type J, let's say J is the type of system. J can be 0, 1, 2, 3, whatever. For the system of type J, steady state error ESS is finite if y of s, y desired of s is equal to alpha over s to the power j plus 1, and steady state error is 0 if y desired of s is equal to alpha over s to the power I, where I is between 1 and j. Alright, so and the steady state error is equal to infinity if let's say y desired of s is equal to alpha over s to the power k, where k is greater than or equal to k is greater than, strictly greater than j plus 1. So what does this say? This summary says that if you have system of type j and the order of your input, if the order of your input is larger, just one larger than the type of the system, then the steady state error will be finite. For example, for type 0 system, step input will result in finite steady state error. For type 1 system, ramp input will have finite steady state error. So, and steady state error is 0 if your type of the system and the order of the input is such that the order of the input is less than the type of the system. So if the order of the input is less than the type of the system and greater than 1, then you will have a 0 steady state error, and you have infinite steady state error if the order of the input is greater than j plus 1. So if you have like let me see if this is even correct. So if I is between 1 and j, so 1 is for step so I can be step, so I can be greater than equal to 1, and I can be less than or equal to j. Yes, so we have this. So if I is between 1 and j, then the steady state error will be 0, even if the I is equal to j. For example, for step input I will be 1, and for type 1 the j will also be 1. So type 1 system we already know has 0 steady state error with respect to step, and this is E steady state error will be infinite if this k is if the order of the input is greater than j plus 1. So hopefully this was informative, and you understood what type of systems have what kind of steady state errors. Before I finish this lecture, I just want to go through with a couple of examples so that you understand the things completely. So let's go with example. So let us suppose we have a transfer function s square plus 3s plus 2, and we use the controller c of s equal 1 over s into s plus 1. So if we use this system is type 1. So this is a type 1 system. So Cg over 1 plus Cg, whatever it is, we don't have to calculate Cg over 1 plus Cg. We can already tell that steady state, so steady state error, E steady state error with respect to step for this system will be 0, and E steady state error with respect to ramp for this system will be, if you take out 1 over s, then what remains is c bar and g bar, and g will be equal to alpha over c bar of 0 and g bar of 0, which will be alpha over this will be 1 over 2, and this will be 1, so this will be 1 over 2, so it will be 2 alpha. So steady state error with respect to ramp for this system will be 2 alpha. Alright, alpha is the magnitude or or the parameter of the ramp input. So let's do one more example. This time I give you CG over 1 plus CG closed loop system. Well, if I give you closed loop system, you will not be able to determine the type. So I have to, even if I give you closed loop system, I have to tell you what the open loop. So if, let's suppose I give you closed loop system s plus 1 over so it will be s square plus 2s plus, let's say 3. So from here it is not easy for you to determine what the open loop gains are, but if you remember that CG over 1 plus CG is equal to numerator over numerator plus denominator, where this C into G is equal to numerator over denominator. So you can use this kind of thing and try to figure out. So you already know that CG is equal to s plus 1 over something, because this is the numerator of s. So if you see, if you subtract x plus 1 from this expression, you will get the denominator. So denominator will become s square plus s plus 2. So this will be C into G, and from C into G you can see that this system is type 0. Because why is this type 0? Because there is no 1 over s that we can extract from this C into G. So for this system, E steady state with respect to step will be equal to alpha over 1 plus C0 G0, which will be alpha over so C0 G0 will be 1 over 2, so 1 plus 1 over 2. So this is how you calculate steady state error with respect to step. We can go through further examples in using exercise problems and assignments. So hopefully in today's lecture you understand how to calculate the steady state error of any given system with respect to step input. So I'll see you in the next lecture.